Well, our title tonight, just by itself, I think kind of hints at the importance of what we're about to talk about. So we're talking about the second fundamental theorem of calculus. It's certainly a foundational concept, one that future concepts will kind of be predicated upon. But real quick recall, before we go any further, I thought a good place to start tonight was, hey, well, if this is the second, what was the first, right? So hopefully the first fundamental theorem didn't sneak by you. The first fundamental theorem was a technique that we used to evaluate a definite integral. So if you recall, if we were integrating, say, f prime of x with respect to x, and we had a definite integral with bounds of a to b, whoops, b's the upper, all right, and that's an a, you would first find the antiderivative, and then we would evaluate that rascal at the bounds. So it would turn out to be f of b minus f of a. And so that in a nutshell is the first fundamental theorem. Sometimes we would delete that middle step and not show it, but I like to show it. And the important concept there was that whatever function you started with here, the function over here on this end would be his antiderivative, and you just plug the bounds in the right order. So that was the first fundamental theorem, and again, that was a technique that we used in order to evaluate a definite integral. So before we get into the second fundamental theorem, I just want to build a strong conceptual understanding of what inverses really are in more generic terms within the realm of math. What are inverses? Well, the first inverse relationship you ever learned was the idea that if you take an x and you add 2, but then you immediately follow that up by subtracting 2, well, you're back to where you started, really, right? Because adding 2 and subtracting 2, they're inverse operations and they canceled each other out. Or a word that I like to use is they undid each other. So inverse functions undo each other. Another one that you learned soon after that was if you take x and you multiply by a certain number, but then you immediately divide by the same number, then again you're right back to where you started. And so you discovered that multiplying and dividing were inverse relationships. A more complicated one was the relationship between natural log and e to the x. Again, the two functions were inverses of each other. Whatever the e function did to x, the natural log function swooped in and undid whatever e had just done, and so you're right back to where you started with an x. And we're going to take that concept with us today, the idea that an integral and a derivative are basically inverse relationships, and that whatever one does, the other one undoes. Is that a word? Am I allowed to say that? I don't know. But there's definitely an inverse relationship, and we're going to go ahead and we're going to investigate that tonight. So before we show you some nifty shortcuts, I want to show you one long example, and I think if you can appreciate this example, you'll have a deeper understanding of the concept behind some of our shortcuts later on in the video. So what they're asking us to do here is the parentheses, if you go back to PEMDAS from middle school, they say whatever's inside the parentheses is what we have to do first. And inside those parentheses, they're asking us to integrate the expression x squared plus 5x with respect to x. Now, once you get done with that integral, they're then asking us to derive that answer. Okay, so I want to kind of see where this whole process takes us. And so if I integrate the inside, I'm going to get 1/3 x cubed plus 5/2 x squared, and because it was an indefinite integral, I do indeed have my plus c on the end. And now they want me to derive the expression on the inside. So if I went ahead and derived the first term, I would get x squared. If I derived the second term, I would get 5x. And if I derived the plus c, I would get 0. So what you'll notice here is we essentially finished right where we started, of course. All right, whatever the integral did, the derivative basically undid it. And so these two operations essentially cancel each other out, just like maybe a natural log and an exponential function do. Now, historically, I've noticed that our students really do a good job with understanding this concept of the second fundamental theorem and the idea that the derivative and the integral are inverses of each other. But they get bogged down with the notation. So before, and I know we're building, and I haven't quite given you the second fundamental theorem yet, but before I do that, I just want to go over some notational issues here. I want to really talk about notation. So first thing, a definite integral as a number. That's basically what you've seen so far. You've seen, nice bounds, a to b, little f of x with respect to x. Now notice in this particular case, both the upper and lower bounds, okay, we'll make a little note here in your notebook, both of the bounds, what did they have in common? They were constants, weren't they? Both the upper bound and the lower bound were constants. And then the integrand right here, this is called the integrand. The integrand was a function of x. So hopefully you can read my writing here. My pen's getting a little worn down. It's close to that time of year where I'm going to have to buy a new stylus pen. Now compare that to this. Now we're going to talk about a definite integral as a function of x. And so it's going to look like this. What if I said capital F of x was defined as the integral from a to x of the function f of t dt? Okay, so now we've got, instead of just having these real cute constants as bounds, you know, integrate from 0 to 1 or from 1 to 5, now we've got the integral as a function of x. This is where things start to get a little crazy, huh? So let's go ahead and we'll talk about this. My lower bound is a constant, so let's get that down. Lower bound, abbreviate bound, that is a constant, just like it used to be. But then things started to radically change. My upper bound was now a variable, okay? And in this case, it happened to be just a very simple x. It'll get more obnoxious than that. Believe it or not, you're going to have upper bounds of like x squared. You're going to have an upper bound of maybe the tangent of x. You are going to see some really obnoxious upper bounds. Now the integrand this time. What do you notice about the integrand that's different than what we had before? Now again, the integrand is referring to this guy right here. The integrand is not a function of x, is it? The integrand is a function of t. And I want to emphasize that the integrand has to use a different variable than the original defined function out front. There has to be a difference. So in other words, if I put x's right here, then that means I'm not allowed to put x's right here. They have to be different variables. All right, so let's put that in our notebook as well. We've got to use different variables. Not to say that the t's will always be t's, but it'll be a variable that's different than x in that particular case. So, goodness gracious, what is the second fundamental theorem? I've been covering every angle, so to speak, just to build up to this moment right here. And here's what the second fundamental theorem says. It says, if you want to derive an integral where the lower bound is a constant and the upper bound is a function of x, alright, and you've got some other function of t right here, then by golly, you really don't have to do that much work. You don't have to do the integral all the way through and then derive it all the way through. Make sure that looks like a t right there, okay? You don't have to do all that much work, because basically what they're going to do is the two operations are going to undo each other. You're going to get f of u times the derivative of u, alright? And let's just clarify what we've got cooking here. U is some function of x. It might be as simple as just x. You know, u might be x. The u could be an x squared. The u could be, x cubed plus, 2x squared plus 1. It could be a trig function. I hope you get, basically u could be anything imaginable that is defined in terms of x. And so we're going to just practice this theorem a little bit. And basically you'll notice there's two things that are happening over here. We are going to, number one, you are substituting the upper bound into the integrand. All right? And then step two is you're also deriving the upper bound. So those are the two things that are really taking place right here. F of u says you substitute the upper bound into the integrand, and then du says you derive the upper bound. So the only thing left to do is to practice a bunch of these. So for our first example, I'm going to try to start off with perhaps one of the easiest example that I could try to think of. Let's say they want me to derive the integral from 0, which is a constant, to x, which is, again, a function of x, of the integrand cosine of t with respect to t. Now that's not the word cost. It's supposed to be the cosine of t, so I'll put parentheses around it. Notice once again that my integrand is a function of t, which is different than the upper bound. And so the first fundamental theorem says we don't really have to do all of the integrating and then the deriving. What we're going to do is we're going to do what I call f of u times du. So f of u means I'm going to substitute this x in for t, and I'm going to get the cosine of x times the derivative of u refers to this guy's derivative, which in this case is just a 1. So the answer would just simply be the cosine of x. In other words, what you'll notice, the derivative undid the integral, and I was just left with the original function, but now it's in terms of x. That's the only thing that really changes. Alright, our second example. I think you're ready to actually try one on your own. This time we're going to integrate from 1 to x squared. Now you'll notice, as long as the lower bound is a constant, it is a non-factor. You just have to do a visual confirmation that it is indeed a constant. Once you confirm that, it does not come into play at all. Whoops. Okay, here's a great point. I made a mistake, and I want you to try to catch my mistake. Maybe you already did. My big mistake right now is that I accidentally put an x right here. That needs to be a what? A dt. So hopefully you can kind of learn from my mistake right there. I wish I would have made that on purpose. It would have been a great teaching moment. So go ahead and try this one on your own. See if you can use your second fundamental theorem to efficiently take the derivative of this integral expression. Alright, so I just reminded myself I need f of u times du, which in this case f of u means substitute the x squared in for the t. So I've got radical x to the 4th plus 1. And the derivative of u in this case is a 2x. And that is it, ladies and gentlemen. That's all there is to these problems. Yeah, sometimes you'll notice it takes you longer to write down the original problem than it does to actually take the derivative. Now, I'm just going to change the notation a little bit, but they're going to be asking me the exact same thing I've done. They're going to define a function. And in the near future, we're going to start to give this function a name. We're going to start to call this guy an accumulation function. So I figured tonight I would start using that name. I won't get into why we call this an accumulation function yet, but just so you know that this is called capital F of x is by name an accumulation function. The big reason why is because it's defined as an integral in terms of x. Alright, but what they want tonight is they want to know what is the f prime of x equal to. So we are doing the same thing we did in the first two examples. They want me to derive an integral. They want me to derive this rascal. So anytime you derive an integral, they're going to offset each other. Yes, our lower bound is a constant. That's great. Our upper bound is a function of x. So when they say f of u, I'm going to just substitute and get the cosine of x cubed. And then I'm going to derive the upper bound, and I get 3x squared. And that, ladies and gentlemen, is the derivative of capital F of x. Okay, before we wrap up tonight, and I think we're doing a really good job so far, I just want you to try 2 more problems on your own that I think have little miniature bear traps in them. So go ahead and try them, and then come on back and see if we both have the exact same answers. Alright, on the first one, again, you've identified that I need the second fundamental theorem because we are trying to derive an integral expression. We know that they're going to offset each other. The only thing I need to do is to substitute the 2x in for t. Now, the mistake is, and I guess what I'm worried about happening is the fact that we need to cube both the 2 and the x. So this is really going to turn out to be 8x cubed. And then don't forget to multiply by your du, which in this case is your 2. Of course, we could rewrite that as 2 sine of 8x cubed. But again, even though the integrand is in terms of t, which it's supposed to be, your final answer is in terms of x. All right. The last one here. What's the first thing that jumped out at you? Hopefully the first thing that jumped out at you was that we need to rewrite the bounds. We're going to negate the integral, and we're going to go from 3 to x squared, and nothing else changes. It's still 8t plus t to the 4th power here. And now I can get ready to go. I'm going to just negate my answer, and I need to do f of u, which in this case is going to be the cubed root of 8x squared plus, what would that be, x to the 8th power. and then I'm going to multiply by the derivative of the upper bound, and that, ladies and gentlemen, is the answer to this derivative question. And so I hope you've built a strong understanding of the second fundamental theorem. I hope you understand when we need to use it and how to use it efficiently so that we don't have to do more work than what's really necessary. So good luck, and we'll see you tomorrow.